Yesterday, we talked about why we don't use an ohm meter to measure resistance in wiring. And this is the example I gave you, is because an ohm meter says this is a perfect connection, and we can clearly see by the picture that this is not a perfect connection. This is one strand of a much bigger wire. So an ohm meter, when I use an ohm meter, it serves as the power supply of the circuit. The ohm meter leads are the conductors, and whatever I'm testing, whether it's a wire or a solenoid or whatever, is the load on the circuit. The problem we have is our normal ohm meters flow a very small amount of current, and we all know that in order to really see resistance, I need to flow enough current through that resistance to get a voltage drop. So since my ohm meter flows such a small amount of current, it really can't sense the voltage drop that I'd have here. It's like, hey, I have this freeway out here and a car can't get through, but I'm going to test and see if we can get a bicycle through or a motorcycle through. Hey, the motorcycle got through, the road's open, right? I mean, what we have to do for work and what the ohm meter does by testing are two very, very different things. So we really want to make a point of doing that. So next we look at circuit function. Now my voltmeter I measure in parallel. So what I'm going to do here is, instead of using an ohm meter, I'm going to use a voltmeter to find a bad spot of resistance. So here I have a similar thing where I have one strand. I have two light bulbs. When I turn the light bulbs in, because this one strand has resistance, it'll have a difference in voltage between here and here, and the voltmeter will see it. And I'm working on a live circuit that's complete, and we're trying to light the light bulbs up. So even if the light bulbs don't light up, because maybe I'm using all my voltage at this bad connection, I will see it with a voltmeter. Where if I disconnect the wire here and disconnect the wire here and use an ohm meter, it'll test just fine. And that's why we don't use an ohm meter for this test, even though a lot of factory flow charts and a lot of documentation says unplug this, disconnect this, and use an ohm meter. Two problems with that. One is anytime we disconnect something, we risk breaking it or fixing the car. The other issue we have is that the ohm meter puts out such a smaller amount of current, I'm going to miss problems. This way I'm testing a live circuit. If my light bulbs don't light up, I'd use a voltmeter across my load and go, wait a minute, I only have 2 volts. No wonder why they don't light up. Then I would use my voltmeter and I'd go from here to battery power, which should be the same, and oh, 0 volts, it's the same. That's not my problem. And then if I went from the negative side all the way to ground and said, oh, there's 10 volts, I'd know, oh, I'm losing 10 volts on my negative wire, and I could isolate and find out where that problem is. So that's why we always want to test a circuit complete. For one thing, it's faster, and the other thing, it's more accurate. So if it's easier, faster, and more accurate, doesn't it make sense to do it that way?
Yeah.
So, and this is something that you really don't see in books so much. Some of them now mention voltage drop testing, but in the real world, almost all resistance faults we're testing using voltage drop. So an ohm meter will tell you which of the following. What do you think an ohm meter tells you based on our conversation at the end of yesterday and today?
Silence.
The second one?
Right?
That is number 1.
First one, number 1. That's right. That's all it tells me. It's connected. It doesn't tell me it's good. It doesn't tell me it'll work correctly. And it doesn't tell me the wiring's good. It only tells me that this end and this end are connected. It doesn't tell me it's good. If you use an ohm meter on a circuit and because you have a good reading, you go, okay, I know the circuit's not my problem, you are going to have a problem fixing cars, because that is a false assumption. So making your head hurt, Joy? And I will have yesterday's video and the day before's video up. They weren't done being edited before class today, but I'll get them all loaded up right after class. They should be done. So circuit tracing. So on the next exercise, we're going to trace parts of the circuit. Normally I would do this in the class because I'd have handouts, but here we're just going to do it together. I'm going to use red for the power source, yellow for switched power, blue for switched ground, green for ground all the time. I'd use orange for varying voltage, AC or DC, and I'll circle the load. So if I look here and trace the circuit, I got my power source. I have my hot at all times section. So that area is hot at all times. Then I have my switched power, my loads, and my ground. So kind of like we were talking about yesterday, where I can define the circuit. And, you know, I love doing this because I break out the highlighters and let you guys actually color to define the circuit. But this is really helpful for what's happening where, because once I do this, now I understand what I should get with my voltmeter based on whether the switch is open or closed. So if my switch is open, I would see system voltage here at the red, but I would see ground here at pin 87. When the switch is closed and we turn the horns on, then I would see power at pin 87, and all this yellow would have power all the way down to my loads. My ground will always have ground. So this is how we figure out, knowing that, now I know what my meter should see. Now I can see if the circuit's working correctly. So for example, right here at pin 87, I have ground right now. If I close the switch, I should have system voltage. Let's just call it 12 volts. So if the switch closes and I only have 10 volts there, doesn't that instantly tell me I have a problem? Right? So then the next question is, where's the problem? Is my problem here at the switch? Is my problem up at the fuse? Or is my problem after the load? But by having 10 volts here tells me what? I have to have 2 loads in series, not 1. And I'm only supposed to have what? 1. So if this is using 10 volts here, then I have 2 volts left over here. Wait a minute, if I got 10 volts here, who stole 2 volts? I would need to go down. Okay, I only got 10 volts across here. If I check between here and here, oh, it's 2 volts. I got a bad ground connection. So you see what I'm saying? If I don't have all of my voltage, that means someone stole some. Right? Because as we studied series circuits, one load has to use all the available voltage. So if my one load doesn't have all the voltage in the circuit, what happened? I have to have a second load. And that second load is normally my problem. That's the load I don't want. That's my loose wire or my corroded connector or something like that. Because I don't have all my available voltage, someone stole some. Are you guys following that okay? Does that make sense?
Well, the question is, this, what we're looking at right now is a parallel circuit, right?
Right. This is the series part, and then this is parallel here, correct?
Okay, so power would have been lost on both sides. The volts would have been lost on both sides,
exactly,
right?
Which you're right. So you're thinking, which means what? My problem would have to be where they have something in common. So either in here or up in here. You're absolutely right. Because if it was just a problem here, that would affect this leg, but it wouldn't affect this. This would still have all its 12 volts. So I'd be dropping 12 volts between here and here with the bad ground. The fact that I have low voltage here, it'd have to be in the series part of the circuit. Because you're right, it's a parallel circuit. If I only have a bad connection on one side, it won't affect the main part that way.
Gotcha.
I love it. That's awesome, because that means you're applying what we've talked about, looking at a scenario and go, wait a minute, it can't be down there. It has to be up here. That's how we fix cars. And the flow chart doesn't tell you that. Understanding how it works tells you that. So you can see where this can really take a lot of the frustration out.
So if there was any problem on ground, it will affect only one of the lights.
Well, they're both are they the different grounds or same ground?
Yeah, no,
Same ground,
what,
right?
what I see here, it look like a different ground.
Yeah, but if you see the line goes across and there's only one number, G104. So they're actually the same ground, even though it's drawn differently.
Oh, okay.
Great point. Because it does, it looks like two completely, but when we started out with series, we ended up actually back at the same ground point. So again,
That's-
back to Mac's question. What do they have in common? It's a parallel circuit. If I'm dropping this, it has to be something in the series side to affect
where
the whole circuit.
That's where the labels and numbers come in handy.
Exactly. And that's why I like doing stuff like this, because it gives us a chance to kind of throw some stuff around and talk and, think about some of the things we're learning and how it might actually help us fix a car that the horns don't work on. Or the horns sound funny. Maybe only one of them's not working. So and if you notice my relay for this circuit is the switch. Now, if I trace the other side of the circuit, I've got power, a load, I got a switched ground, and then constant ground. So this is my horn switch, which is in my steering wheel. It goes through what's called a clock spring, which is the part in the steering wheel that allows me to turn the steering wheel around and still keep an electrical connection and not twist the wires up. And in this case, we're going into a module here that turns on the relay. But this is the switch ground side of my circuit. So on this part right here, if this is open, I probably have power here. When it closes, I would see ground here. And even though a computer is doing this, normally a computer will still put voltage on this line through a resistor so the computer can tell when things changed. Also, it uses it for setting codes. So, right, so I have two circuits on this schematic, right? I have a circuit here, and then I have a parallel circuit over here. But on this circuit, this is a switch. Here's my two loads. On this circuit, here's my load. My switch is all the way down here. So this is a ground switch circuit where the previous one, oops, didn't want to do that. Previous one was a power switch circuit. So I can control a circuit by switching power or control a circuit by switching ground.
When you have a ground switch, your current is always there. Then your voltage.
Yeah, voltage will be at the switch, and I collapse the circuit back to the load when I apply the ground. So this would see power. This would have power potential in it right now. So I'd have a 12-volt difference across the contacts of the switch. But as soon as I close the switch, this would all go to ground all the way up to the load. So I don't have current flow until I close the switch. What I have is voltage potential. Did I answer the question okay, Gabriel?
Yeah,
Yes, yes.
voltage potential because it's not running, right?
Exactly, because it's not a complete circuit. So we say that's potential because I'm not dropping any voltage to the load. Once I have a complete circuit, I'm going to drop all my voltage to the load. So I can see voltage potential there. My voltmeter is going to say there's volts there, but there's really not volts there that I can really use to do work with.
So the wire's not live?
Well, the wire is live in that it has power in it. But if I ground it, I'm not going to create a dead short. I'm just going to create a completed circuit. Where if I have a live wire without a load, then that would be a short. Now we start melting stuff or blowing fuses.
Oh, okay, I see.
You see, kind of see the difference there. It gets a little confusing, but that's why I'm using the term potential. If I put a DVOM there, I'd see 12 volts. But I don't have 12 volts that I could necessarily light a light bulb up or run a motor with because there's a load in the circuit already.
It can't go anywhere.
Yeah, exactly.
It's at the horn on the bottom where you switch it. Where you
Where
turn
I
it.
complete the circuit, right. I complete the circuit through here, which means then what? The ground is going to come from my ground all the way up through the blue, through here, all the way to here, so that I can drop all of my system voltage across my one load in the circuit. So if I had a horn that didn't work and I wanted to test this relay, and I love using relays for testing because you think about it, this is inside the steering column. The horns are underneath the car or behind the grill. They take a while to get to, but this relay is in a nice box underneath the dash. It's really easy to get to. And here at the relay, I can see, do I have power going to the relay? Do I have a signal here that should be ground when we push the horn button in? And do I have power coming out on pin 87 when we do? I could also just jump her from pin 30 to pin 87 and the horn should make noise. So instead of tearing the car apart, I can go to this relay and I can test this whole circuit, both circuits, from that one central test point to figure out where I need to go do more diagnostics, or do I just have a bad relay? If I go to the relay and there's no power here, what? I need to go up and look at the fuse. If I'm looking at the relay here and there's no ground coming here, I'd have a couple choices in this car. One is, this is a module. If it's a module, I might be able to talk to it with a scan tool. So the scan tool might tell me if I'm pushing the horn switch down or not. On this car, it actually does. So I could use the scan tool and push the horn button and say, does the computer see the horn button being pushed? Because if the computer sees the horn button being pushed, but it's not putting ground here, I need a new computer. Or I got a bad ground connection on the computer. But on the other hand, if I'm pushing the button and nothing's happening, now what? I need to go test the horn switch or this clock spring to see if that's the problem. So by testing something at a central location, it gives me a direction. If this is working and power's going here at pin 87, but the horns don't make noise, now it's time to go test the horns, isn't it? But now I've justified taking the bumper off or going in and putting the car up to get to those horns to test them. So you see why when we diagnose a vehicle, we really try to look for central test points that are easy to access, so I can try to get as much information there, use the wiring schematic to figure out, where do I go? Do I go here? Do I go here? Or do I go down here? Well, if I go in the middle, now I can figure out which direction I need to go. Traditional diagnostic testing has you start at the fuse and then go all the way through the switch before you ever go over here, or they'll have you come down here and backtrack. So you spend a lot of time, it's that linear, you start here and go here, don't miss any steps. Well, why don't I go in the middle and figure out what I have, and then I can figure out which way I need to go, and it's going to cut my amount of time in a half or a quarter. Instead of, I'm on step 12, I got 26 steps to go. How do I can jump somewhere and now each way only has 5 steps? Now I'm going to fix it in 6 steps instead of 20. So I kind of try to, you know, when I go over this stuff, a lot of it, I wanted to get you guys thinking about what you can do with some of the stuff we're learning and why we're learning it. So I do have this chart in here. Talks about limitations and alternatives for resistance testing. Wiring, switches, and connectors. Use the voltage drop method. Don't use an ohm meter. Sensors are about the only components where a resistance test might be a good idea, but it's still better to disconnect the sensor, backfeed voltage in the harness, or use a signal generator where we use that in place of a sensor to see if the computer can read the circuit correctly. I can have sensors that ohm out good, but don't work. So great, if I ohm it out and it ohms out really bad, I found a bad sensor. But if it ohms out good, I haven't proved the sensor's good. I'm just back to square one. And what we do at a more advanced levels, we actually just use an oscilloscope and hook an oscilloscope up. We do that for wheel speed sensors. So if I think I have a bad wheel speed sensor on an ABS system, I'm not going to ohm it out. I'm going to hook a lab scope up and see if it makes a pattern. If it doesn't make a pattern, I know the problem's at the sensor. If it does make a pattern, but the computer doesn't see it, it must be in the wiring or in the computer itself. So now I'm going to check where the wiring goes to the computer. Do I see my signal there? If I do, the problem has to be in the computer. So now in 2 steps, I figured out that I got a bad computer. That's pretty quick and easy, but I could do that with a scope. I can't do that with an ohm meter. An ohm meter, I'm still guessing. On the other hand, if I check it with a scope and the sensor doesn't make a signal, I have to ask, is it a bad sensor? Or is it a wheel or something that the sensor's looking at that's broken, or a magnet fell off or something like that? So then I would want to do what? Probably recommend a new sensor, take it off, inspect, make sure things are at the right place. I would at least be looking for those things. And you laugh, but we do have magnets fall out of things inside engines. I put 5 sensors on it, still has the same code. We take the sensor off, walk the engine around. Yeah, the thing the sensor's looking for isn't there. That's why the sensor doesn't tell you anything. The sensor has nothing to say because there's nothing there to talk about.
That's interesting.
But with using a scope, you know the sensor is not generating a signal. So your automatic thing is, okay, if the sensor is not generating a signal, get me a new sensor because it's probably bad. But let me make sure that what it's looking at is actually in the correct place. So that's the, that's the neat thing about applying, and what allows us to use a scope is Ohm's law. A lot of patterns we have when we look at actuators, we're only turning things on for 2 milliseconds, 2,000ths of a second.
Mr. Bryan,
But with a scope, I can use Ohm's law to see if it's good or not. Yeah, Gabriel.
I had a problem with my truck, and it was going from 5 miles to 50, back to 20. So I took it to the shop, and the guy said, look, right there where the sensor is, there's some leak of oil. If you clean it, or it might catch when the flywheel is turning. So I did that, and it just went back to normal speeding. But sometimes oil on the part of the sensor might misread it.
Yeah, and it's not just the oil. What it is the metal particles and dirt that the oil collects. So the oil itself normally isn't the problem. It's all the junk that the oil brings with it.
Yep.
But I've also seen, like on ABS systems, where the little ring on the axle gets a crack in it and breaks, and now it moves, or it does, and it causes all kinds of weird problems. Boy, the sensor ohms out perfect. Bulbs. You can check a bulb for continuity or power with jumpers, but the actual resistance is so much different than how it works in the circuit, that the value is useless. In actuators where the computer or something's being turned on, we would want to use voltage drop to see if it's working, right? If I have 12 volts and it doesn't work, it's bad. Why would I want to use an ohm meter to test it? On the other hand, if it has 2 volts and it doesn't work, it doesn't have enough voltage. Let me go find out where my voltage is. And so that's why we wouldn't use an ohm meter to test actuators, even though most solenoids and actuators, the manufacturers give us a specification. So voltage drop testing. Voltage drop only drops in a complete circuit as current is flowing through resistance and work is done. In other words, the voltage is converted to work: heat, light, motion, sound, force, etc. Voltage cannot drop in an open circuit. The open circuit tests still have their place because we can see the difference in voltage potential. Voltage drop can only be measured in a complete circuit. If the circuit isn't complete, you're measuring voltage potential, not drop, although we use those. The test is the same. We use the term separately. What you need to understand is if I'm seeing the drop on an open circuit, I haven't tested the rest of the circuit. I've just found the open, because I can't drop through any other resistors. If it's a complete circuit, now I can see all the resistance in the circuit. So here's an example right here where I'm looking at voltage drop, and I'm going from negative to battery positive before the load in a complete circuit, and I have 12 volts there. Well, since I have a 12-volt battery, because all my pretend batteries are 12 volts, I have all my available voltage, I'm good. But if I only had 11.8 volts, that means someone's stolen some of my voltage. If I only got 10 volts, someone's stolen some of my voltage. So this lets me know that this wire and this switch is all good. Now here's voltage potential right here. In this case, I'm measuring from ground to the potential battery positive because I have an open circuit. So as we've gone through the load and all the way to here, we haven't used any of our voltage because I can't drop voltage through a resistor if there's no current flow. So I'd see 12 volts there with the switch open. What's going to happen when I close the switch? Which voltage going to read?
Zero.
Every
Zero.
12.
Exactly. And that's what I was saying. It's really important when we look at test points to understand the state of the circuit we're testing. Because here I'm at one test point. I'm going to get 12 volts with the switch open, but 0 volts with the switch closed if the circuit's good. So obviously, if I close the switch and I have 6 volts there, that means I have to have a bad ground. I have to be using 6 volts between here and my way back to the battery. So you can see where this is a real powerful test because it really lets me know what the whole thing looks like, how the whole thing's working. I'm no longer looking at, is this little part good and is this little part good? I'm able to look at the whole thing very quickly and say it's good, or we have a problem and I need to go find it. Remember what do I say? How do I get the most information with the least amount of work? To me, this isn't a lot of work, right? If I can do 1 or 2 tests and figure out it's either good or bad, that's huge. And the big thing is I don't have to take stuff apart to do these tests normally. So I do have some specifications just for reference here, because what we're doing on paper is different than what we get in the real world. So on paper, my switches are perfect. All my wires are perfect. My connections are perfect. Because, you know, it's about learning the principles. In the real world, if I'm doing a test, if I lose 300 millivolts through a switch, that's perfectly acceptable. So say I have, 13 volts going into my ignition switch and 12.7 volts coming out. I'm not going to sell an ignition switch for that. That's an acceptable amount of voltage drop. Wire. Normally we allow about 100 millivolts in a wire, but 200 millivolts max. Some battery cables while starting are allowed 200 millivolts. The only exception to that is the charge wire for the alternator that's allowed 300 millivolts. Connections, we allow 100 millivolts per connection. Module connections are a 10 millivolt max. So we really care about good connections going to computers. So you can see here, if I have a circuit where I've got a couple connections and a switch, I might lose half a volt or 0.7 of a volt going to my horn. So instead of my car is running, instead of 13.5 volts going to my horn, maybe I only have 12 or 12.5 volts going there. Horn's still going to work. That's not my problem. You know, if I add up some connections, add up some wires, got a switch, I've lost 0.7 of a volt. That's probably not my problem. For everything to be high is definitely on the high side. But one thing I always ask when we're doing testing is, how's the car run? Oh, it runs fine. Then don't worry about it. Yeah, but it's out of specification. Shouldn't we fix it? No, it's fine. The car runs fine. The customer doesn't have any problems. You're not having any problems. Don't look for problems. And I learned this the hard way, because there's nothing worse than selling it because it's out of specification. And guess what? Guess how good the new part is?
It's just like the other one.
No, my luck, it's usually worse.
Oh, God.
So it's like I'm going downhill here. I really tried to do the right thing. I really wanted to make this good. And I did this, and I've actually made it worse because the part I had was actually better than the part I bought. And that's why I say, so, I mean, there's things that are out of specification. And then there's things that are causing the problem we're trying to fix. And we need to constantly be asking, great, I found something out of specification. Is that causing the problem that we have? If it's not, make a note and move on. You know, a lot of times I see people test because they want to test everything when they start learning about testing. And they got a car with a whole bunch of new parts and the car still runs the same way. Well, yeah, those were technically out of specification, but it wasn't causing the problem we're experiencing. We haven't fixed the car. And you think about it, if you're a customer and you're getting your 5th phone call about the new part they found because it still runs the same way, but the last 4 parts the car really needed, how much confidence do you have in that technician or that shop? You're having some real second thoughts, aren't you? And then if the 5th part fixes it, did I really need the first 4?
No.
Okay. And that's why we test and don't just replace. And testing is all about asking questions. What did I tell you guys the first day of class? It's my job to get you to ask questions and give you some tools to find answers. That's what we're doing here. So, again, specifications on a previous slide are for circuits that draw over 1 amp of current flow. For sensors that flow milliamps, the voltage drop would be considerably less with the same unwanted resistance. Remember, the more current flow I have, the same amount of resistance is going to have a bigger effect on the circuit. So what is the maximum amount of voltage drop that's allowed to be present across the switch contacts?
300.
300. You got it. And if you notice, I put both here, 300 millivolts and 0.3 volts. It means the same thing, but as we move on in this class, I'm going to be giving you either one or the other on things. I need you guys to be able to move those two back and forth and understand those are the same thing. So right now we're learning. I try to give them both. In a couple weeks from now, you may only see one or may only see the other because that's how manufacturers give us specifications. One manufacturer may say 300 millivolts. Other manufacturer may say 0.3 volts. We need to understand those are the same. You know, just like 12 and a dozen, and we're not talking baker's dozen here. Had someone bring that up. What about a baker's dozen? We're not talking about those. So here's an example of a vehicle that has a voltage drop across the switch contacts or the wire. So I've got 12 volts between my battery negative and the switch. Now, after we go through the switch contacts all the way up to the bulb, I only have 11.8 volts. That means what? Someone stole 200 millivolts. In this case, I'm suspecting the switch, and that's below my what? My limit. So that's okay. It's okay not to be perfect. I don't need to go buy a switch. I just need to understand that's where it went, if that's where it went. So what I can do, I can test. So in this case, I've got 12 volts to here. Now I've taken my meter and I've gone from the switch to here to 200 millivolts. What, could I go to the other side of the switch to see if the 200 millivolts is in the wire if I wanted to? Yeah, and that's what you do is you just move these two leads closer and closer together to isolate where the bad connection is. And I would do that at different connectors or different test points. So I'm not adding 200 millivolts to 12 volts. I'm taking it away because I used 200 millivolts between here and here. Remember what I said? The meter measures the difference between 2 points. The difference between the point here and the point here is 200 millivolts. We saw on the previous slide that when I compare the difference to battery negative, it's 12 volts here and 11.8 volts here. But the difference between here and here is just 200 millivolts. And that's why I only have 11.8 here. I had 12, I just used 2, I got 11.8 left. Got a hole in my pocket. Some dimes fell out. So here I'm doing a voltage drop across a load in a complete circuit. And we can see here that the bulb's working and it's getting all my 12 volts. No one else is stealing voltage here. If I start my battery with 12 volts, which here I did, and I still have all 12 volts at the light, no one stole any voltage. So what I did is didn't I just test all the wiring from here to here and from here to here and my ground connection all by just hooking my meter up right here and seeing if I have the same voltage I have at the battery? Isn't that a lot quicker than trying to test all the wires?
Definitely.
And now let's look what happens if my bulb's bad. I still have 12 volts here because now I see the potential between here and here, which means what? My voltage drop across a load in a complete circuit is the same whether the load's working normally or whether the load is bad. And I just used a burned out light bulb here, but this could be a bad solenoid, could be a bad motor, could be a bad anything. I've got 12 volts and it doesn't work. It's bad. Why would I waste time going and trying to find an ohm meter specification? I mean, books are great. AllData, when they first came out in 92, 93, I think I bought it right around then. It was a year or two right after when it first came out. At that time, they had 8 million pages of information. Do you think that number's gone up or down since then?
Yeah.
Up exponentially, I bet. So we're looking at millions and millions of pages of information. And it takes time to navigate that. It takes skills to navigate that. But if I don't have to navigate that, haven't I just saved time?
Yes.
If I do this test right here and hey, your light bulb, motor, solenoid, whatever doesn't work and it's got 12 volts, you need a new one. I'm done. Why do I need to go spend 10 minutes looking something up in a computer system trying to find a specification so I could disconnect it and put an ohm meter on it that may pass an ohm meter test? I already proved it doesn't work. Who cares? Give me a new one. Is this making sense to y'all?
Yeah.
Kind of a
makes-
different way of testing,
Yes.
isn't it?
Yeah. So how would
Kind
you
of
know, like,
What's that?
how would you know when to use a scope or something to know if that bulb is bad or not?
Okay, good rule of thumb. On slow circuits like this, I'm probably using a DVOM. If it's just a simple on-off. If it's something that turns on and off quickly, or it's something I need to turn on and off like it's momentary, where I can't be in two places at once, I'd use a scope or graphing multimeter. So that way I can take a movie, go back and look at the movie and see, did I get my voltage or not? So what the voltmeter, so I could use a voltmeter or a scope. On a slow signal like this, I'd probably just use a voltmeter or the voltmeter setting. If it was a faster signal like a solenoid or a maybe even a motor, depending on how I'm controlling it, or if it's something that like a windshield washer pump, right? I hit the button and it's supposed to pump. Well, I'm by myself. I can't be out there and up here. So I either need to have a meter with long enough leads that I can put it in the windshield so I can see it when I push the button, or I could use something like a graphing multimeter or a scope and have it take a picture of 30 seconds of time and then go inside and push the button down and hold it down for 5 seconds, come back out and see, did it have 12 volts there for the 5 seconds when I push the button? So that's what I'd use, something like a scope or a meter, because the scope or graphing multimeter allows me to kind of be in two places at once. On a fast signal, it's the only way to do it. On something like this, it's a light bulb, it's slow. I could use a DVOM, I could use a graphing multimeter, whatever I'm comfortable with. Does that help, Miguel?
Yes, thank you, Brian.
Okay. So that is, so like I said, so a lot of stuff I look at is kind of this way. I'm not the sharpest knife in the drawer, but I can figure out if it's got, if it's got 12 volts and it doesn't work and it's supposed to have 12 volts, I need a new one. And I had students a couple classes ago were diagnosing a electric cooling fan for a radiator. And it was for one of the guys that works in IT at the college. And he came up to me, he goes, we told him it needs a new fan motor. And he goes, well, what's wrong with it? Is it like the brushes or the armature or commutator? Or where do you think the problem is there? And I finally looked at him, I go, look, it has power and ground and it doesn't go roundy round. You need a new one. I don't care what's bad inside. It can be out of pixie dust for all I care.
Yeah, that makes completely sense.
I mean, we can marvel in how much we know about what goes inside, but at the end of the day, I don't care if the light bulb's filled with magic pixie dust or a filament. If it has 12 volts and it doesn't work, I need a new one. Going back to what I said, what do computers work on? Smoke. You know, if you remember that, you can fix cars. I mean, do I know a lot of what goes on inside a computer? Yeah, I do. But for the purpose of fixing a car, I just remember they work on smoke. When the smoke comes out, it don't work. And I fixed a lot of cars over a lot of years remembering that. So, you know, sometimes it pays just not to be too technical.
The combination of logic and simplicity, I guess.
Yeah. I always tell people I'm just a dumb guy that tries to fix cars, and some days are better than others. Right? Lawyers practice law, doctors practice medicine. I just practice fixing cars. You know, for some reason, when we fix cars, we're thought we should be perfect. It's an exact science. No, it's not. I have books here that are they're 40 years old, actually 60 years old. How we thought things worked even 20 years ago is completely different than how we know they work now. We're constantly evolving.
That's true.
So in a series circuit with a single load, the voltage drop will be the same across the load, whether it's working or not. Well, we just proved that's true, didn't we?
Yeah.
That's like a silver bullet for fixing stuff right there. My window doesn't go up. Okay, well, let's go measure the voltage at the motor on the window. Hit the button. Do you have 12 volts there? Yeah. Does the window move? No. Looks like we need a motor.
So true.
If I don't have 12 volts, let's go look at the switch or let's go look at those things. But it's, you see why going to the load when you diagnose something is so important. So the two things I like to look at is relays, because relays a load for the control circuit. And if I don't have a relay, it's just a simple circuit. I'll go to the actual load I want to test because it's the quickest way to figure out what's wrong. So now I've got some exercises for us. So this right here, what I want you to do is I want you to look at number one. And if my positive lead of my meter is here and my negative lead of my meter is here, how many volts am I going to have here? I want you to do the same thing for number 2, 3, 4, 5, 6, 7 on this page. Keep in mind my switch is open. I'm going to give you guys a couple of minutes to do that, and I want to go over this with you. Because this is how we test cars. Okay, I see someone told me what they got for number 1.
0.
12.
12, 0, 12. Okay. Well, let's think about it. So number 1, the red side is on 12 volts, correct?
Yes.
And the black side is a ground, correct?
Yes.
So the difference between 12 volts and ground is
A complete circuit.
complete circuit, 12 volts.
Well,
12 volts.
So what's number 2?
See,
12 volts.
Well, so right here is 12 volts.
Zero
Right
volts.
here is 12 volts. What's the difference between 12 volts and 12 volts?
Zero.
0. So we see 0 volts there. Remember, the meter measures the difference between the test points.
Why is this?
oh, okay.
We're not looking at the absolute. You guys are right when you're thinking in your head, wait a minute, I got power there. You're right. What I'm looking for is the difference between where the 2 meter leads are. So going with that, what's number 3 going to read?
well. 0.
0, right? Because I got 12 volts here, and I got 12 volts here because my switch is open. So I'm going to have 12 volts all the way to the edge of the switch. And when I do this in class, I actually have you guys highlight where the power is and where the ground is and where the switch power is to kind of help
Yes.
with this.
It's open.
And
Open is 0.
so, yeah, 0 for number 3. How about number 4? What's number 4 going to have?
12.
Good one.
Number 4.
Difference.
It's
12.
It's
12.
Right, because I got what? I got 12 volts coming all the way to the end of the switch, and I got ground coming up all the way to this side of the switch. So if I go from this side of the switch, which is 12 volts, to this side of the switch, which is 0 volts, the difference is 12 volts. So what is number 5 going to read?
12.
0.
0 volts.
Has to be
Zero is
0
just-
because I'm on this side of the switch to this side of the switch. I'm on the ground side. Ground minus ground is 0. One way of thinking about it is if I take the positive lead, wherever it's at on the circuit, and subtract what the negative circuit reads, the difference is what the meter reads. And it's not an exact way, you know, but it's a real good way as far as for these exercises to kind of understand. So in this case, how many volts am I going to read on number 6?
0.
0, right? Because I have 0 volts minus 0 volts is 0 volts. And what's number 7 going to read?
0.
0.
0.
Absolutely. So now let's close the switch and see how it changes things.
Nakuha ko na eh.
And I'll give you guys a couple minutes here.
Wala naman siya.
Okay, okay.
Isinulat ko na diyan.
Okay, okay, okay. Okay, number 1 is, inulit niya uli. Kunin mo uli yan. Inulit niya uli. Kunin mo uli yan.
Nakuha na.
Iba yan eh. Ay, patayin mo.
How can I enter there? It doesn't take the reading.
What, in the chat? It won't let you enter?
Oh, chat. Yeah, you're right. Thank you.
Not a problem. I try to help. Some days I do better than others, I think.
दानिया ये जल्दी से हटा दो दानिया come here
Okay, so what did we get for number 1?
12.
12. Okay, what did we get for number 2?
0.
0
Okay. How about number 3?
0.
Number 4?
0.
12.
12.
4 is 0. We're just going across a fuse. A fuse is not a load.
0.
0. What's number 5?
Number 5 is 12.
5 is 0
5 is 0 because the difference between here and here is 0.
Oh,
Number 6. What's number 6?
0.
12. It has to be, right? Series circuit. Doesn't the series circuit rule say in a series circuit with a single load, my load has to use all of my voltage? So unless I'm on either side of the load, I can't get 12.
yeah
So what's number 7 going to be?
12. I mean 0.
0, right. So now let's put in 2 loads. But the circuit is what? Open or closed?
wala naman.
Open.
Open.
Open. Okay, is that going to make a difference on what my readings are?
Yeah.
Okay, so let's go ahead and give you a couple minutes to this page.
Kasi wala yung...
I need to do more of these.
Sagutin mo ngayon yan. Number 3 exercise. Kinuha mo yan, di ba?
Oh, pero hindi ko iko na litrato yung...
Exercise.
Okay, so that one...
Yeah, see, this is very different than the homework where you're just solving for the unknown. This is actually using a meter to figure out what your expected voltage should be.
Na-cut off dyan, di ba?
Sagutin mo. Kung tama ka. Ang answer dyan eh.
0. 0, 0, 0. 0, 0.
I saw Jose's comment. That's awesome.
5 is a 12. 12.
हम इधर कह रहे हैं तो नहीं कर रहे दानिया
Okay, all zeros, I think. This
I
is
only see 112.
Kinuha mo yan?
Yeah, I think.
Tignan mo ng answer mo kung gusto mong answer. Chat, mag-type ka 0, 0, 0, 0. So, kung gusto mong answer yun, yung 0.
12 lang, ang number 5 lang ang 12. Kasi it's continuous, right?
Kung gusto mo
Okay, so what do we get for number 1?
12.
0.
That has to be 0, doesn't it? The switch is open. So this is going to be ground and that's going to be ground. That's 0. I can't drop anything through a resistor. How about number 2?
0.
0.
How about number 3?
0.
0.
How about number 4?
0.
How about number 5?
12.
12. How about number 6?
0.
0.
How about number 7?
0.
0.
Oh, you guys are making this too easy. So let's close the switch so you can actually do some math. I'll be right back.
Okay. Another series yan. Sagutin mo nga.
Iba naman ito.
Close niya yung switch eh.
4. Okay. So 1, 2, 3, 4, 5, 6, 7. Okay, yes, number 1 is 0. Ayun na, 12. 12. 12, kasi walang open circuit. 3, 12. Number 4 is 12. Okay, oh, 12. 12. 12. Hindi ko makita yung bandang iba.
0 and 5.
Why? There's no open circuit.
0 and 5. Ikaw, ilagay mo 0 ako, ikaw 5.
Hindi, number 5 is 12 ako.
Okay.
Ikaw, 0?
Number 6
Okay.
is 0.
Right.
Pero nakita ba ito sa isa? Pero akong question sa kanila.
Switch. There's a volt at the switch. Bakit may formula pa ba yan? Tingnan mo lang yung litrato.
Okay.
Ano? Ano, sir mo?
Saan? I-mute mo.
Okay, so what did we get for number 1?
12.
6.
Okay, well, let's think about this. If I did 12 volts here, what's this guy get to eat?
Yeah, nothing.
Yeah, that can't work. And these guys are equal, aren't they? So I can't feed one of them and not the other. I got to what? Feed them equally.
Yeah.
So what do I need to do? I need to figure out my current flow in the circuit. So how do I figure out current flow?
Well, divided by 6.
Right. I got to add my resistance, 6 plus 6, 12 ohms. 12 divided by 12 is what?
1.
1. So 1 amp. Now I can take my amps times my resistance. 1 times 6 should equal.
6.
Everyone see how I got there?
Yeah, I got 6 also.
Okay, cool. I knew some of you did. I could see that coming in, but I saw a lot of you didn't.
Oh, I
Well,
got
this one right here, what do you think we have here for number 2?
8.
Kunin mo yung pag nag-answer siya.
6.
6.
Okay, well, let's just do the math. 4 plus 8 is
12.
12. 12 divided by 12 is
1.
1. 1 times 4 is
4.
Any guesses what we get for number 3?
Oh,
12.
10. No.
12 times 1.
1,
10.
10.
2, right?
Oh, what do we have? We have 2 plus 10 is 12. 12 divided by 12 is 1. 1 times 10 is
10.
10.
Okay.
How about number 4?
So, 12, 1,
Okay.
6.
6.
6. If you notice how mean I am, I made all these add up to 12 for you. What do we get for number 5?
0.
0. Good job. Number 6.
6.
Well, let's do the math.
2,
6 plus 6 is 12. 12 divided by 12 is 1.
1.
And where's my meter? It's going from here, 6, plus another 6. So my meter is going around 12 ohms. 12 times 1 is,
12.
what do you think we have for 7 then?
12.
12. And it really doesn't matter, these last two, what the resistance of those is, because it's my only resistance in the circuit.
6 is the number 1.
It could be 6,000 ohms of resistance. It's still going to be 12. Okay, so you kind of getting the idea how we're doing this now?
Yeah, I
So
need
now
more.
let's take a look at what happens on a circuit where I have some unintended resistance. So we know what 2 light bulbs or 1 light bulb look at, but in this case, I got 2 light bulbs in a bad ground with 4 ohms. Here I got 2 light bulbs in a bad switch with 4 ohms of resistance. Here I have, again, a bad ground. And here I have a bad wire with 4 ohms. So we're going to do the same thing here that we did on the last. We're going to add up all of my resistance in the circuit, including my bad, ground or wire that I don't want, figure out my current flow, and then take the current flow times the resistance that we're measuring around to get the voltage reading. So I'll give you guys a couple minutes here.
This is confusing.
Okay, well, that's why I go over it. If it wasn't confusing, I wouldn't have to teach it to you, right? Because you'd be able to figure it out yourself,
Yeah, BASE certified.
right? And that's why I'm trying to help you guys. I know that's what you want. Like I said, I just had to do my ASE tests again, and I had to do 22 of them in December. So,
Brian, I guess to figure this out, as long as you know the formula, right?
yeah, you just add up all the resistance,
Yeah.
total resistance, divide your voltage by resistance to get your current flow, and then you multiply your current flow by the number of ohms that the meter's going around.
I got it.
So,
Okay.
So like this first one, what'd you guys get?
12. 5.
Well, it should be 12, but it's not because I have what? A bad ground. So how many ohms do I have? I have 4 plus 4 plus 4. I have 12 ohms of resistance. 12 divided by 12 is 1, right? So, and how many ohms is my meter going around?
8.
8. So 1 times 8 is
8.
8. I'll give you guys a couple minutes to do these, finish these other ones. Now you can see how I did that one.
I see where my problem was. Now I kind of see it. Just got
Right, that's why I did the first one, and I'll let you guys go back and rework them a little bit.
Oh, it's getting fun now.
Yeah, I mean, like I said, it's all learning, and this is, you know, we look at this, and is this hard? Yeah, it is. I do this exercise with people that have been doing this 10, 20, 30 years, and they struggle with it and get it wrong. That's why I'm teaching it to you now, because I know how important it is. I know how much this has helped me fix cars and helped me pass tests and so on. Why would I keep it from you just because the book doesn't teach it to you?
The second is 4 and the third is 4.
Number 2.
The fourth is 6. Fourth is 12. Fourth.
Daddy? कैसे को? Your mother?
I'd like the question number 4. Question number 4 is a 3 volt.
No, it's 4.5.
Okay, well, let's take a look at number 2 here. So how much resistance do I have total in number 2? 16, right?
16.
So 12 divided by 16 is what?
0.74.
1.4, right?
0.75 or 3/4. I mean, I can just reduce it as a fraction, right?
Yeah.
So I can reduce it to 3/4, or I could get, once I get to 3/4, that's 0.75 either way. So what is 0.75 or 3/4 of 4?
3.
3.
Number 3 is 4.
Number 3 is 4 because I got 1, 2, 3. So 12 ohms resistance. 12 divided by 12 is 1. 1 times 4 is 4.
4.
Does it help me having the answers up on the PowerPoint as we go through?
Yes.
Okay. Because that was something I didn't add to, I think, 1 or 2 classes ago. So this last one, what's my total resistance of the circuit?
4.5.
Right, 16 ohms, right? 12 divided by 16 is 0.75 or 3/4. So 6 times 0.75 is, and I already heard the right answer a couple of times.
18.
4.5.
4.5.
Yes. 4.5.
So this exercise kind of help you as far as when we talk about test point voltages and how my meter should read across the circuit and how whether the switch is open or closed, it really changes what the meter reads, doesn't it? Now, all these PowerPoints are on Canvas. And I have a lot of notes in this PowerPoint presentation.
Yeah.
I think this for like practice homework or something like that would help me specifically.
Right, and I used to give this as I tried giving it as a homework, and people just really got frustrated with it. And then I did it as an in-class exercise and had them turn in. And I haven't drawn up another one of these yet that I could give as another homework exercise, and I need to do that. I'm still playing catch up, trying to get all this stuff ready for online, because a lot of the stuff I had on campus, I got to kind of try to convert or figure out another way to do it. But no, I'd like to do more of this, and we will do more of this type of stuff as we get into sensors and we start looking at sensors. We do a lot of this type of testing because this is how we test sensors. So we need to be able to understand what we're going to get at different parts at different conditions. So we're going to be coming back to this quite a bit throughout the class. But I agree, more practice would be better.
I have a question on number one. On number one, if you take off the 4 ohms that is losing on the ground, you
Right,
said it would be 12 volts. Is
right.
it?
Yeah, if I didn't have a bad ground, we'd have 12 volts. But since I have a bad ground, now I only have 8 volts.
Okay, thank you. Just
And
wondering.
where that's important is, remember I said General Motors, and they're a fairly good sized car company, says if it's less than 5 ohms, it's not a problem. Well, we can see here 4 ohms takes me from 12 volts down to 8 volts. So imagine this was my fans on my radiator. Do you think they're going to spin a lot slower if they only have 8 volts than if they had 12 volts?
Yeah.
Yes.
Okay. Could that cause my car to overheat?
Yep.
Yeah. So think about it. We have a car that's overheating, and the customer's already put a new thermostat in it because, of course, that's the first part we replaced that we guessed at. Then we put a radiator cap on it. Then we put a new radiator in it. Maybe we even tried some new fans because they didn't look like they were going fast enough. So now we're into this thing over $1,000, and it still overheats because no one bothered to check the voltage drop across the load.
Yeah. That's true.
Into my Cavalier.
So you see where this has a real practical application?
Oh, yes.
I can see Joey, he's really thinking here. I can see the gears turning.
Yeah, you know, when you walk the formula step by step and get your answer, you know, so I could see how you walk to get the answer, you know.
Right. And I know you missed yesterday. I went through a whole bunch of real good stuff yesterday, so I'll get that video up today, Joy, so you can take a look at it.
All right.
So here we talk about resistance test with an ohm meter. Can I use an ohm meter? Absolutely. So I would need to turn my dial to the ohm setting where I have the arrow going, and we would connect our leads between the common and where I have the ohm symbol right here. So that's where my leads would be connected, and I would get a reading up here. And then I could ohm out a wire. But to ohm out the wire, in this case, I have a fuel injector. I need to disconnect the wire here, disconnect the wire here, and then it tells me, oh, I have 0 ohms of resistance. Does that mean it's going to work? I have no idea. Because we saw in the example of just that little strand twisted together, I'm still passing this test. So this doesn't tell me if it works or not. That's why we use voltage drop. But this is, if you hear me talk about, if I'm using an ohm meter, whatever I test, I have to isolate from the circuit. Well, isn't a lot more work to disconnect it here and go find the other end and disconnect that there and then ohm it out, and I still don't really know if it's good. Or I could just leave everything connected and measure the voltage from here to here by back probing it while it works. And in this case, I would use a scope because an injector is a very fast signal. I could disconnect it and measure just the fuel injector and get a specification. And this one's 12 ohms, and that's about what they normally are, is in that ballpark. Normally injectors flow about 1 amp each. Actually, working resistance goes up. They end up flowing about 800 milliamps. But injectors aren't real easy to get to, are they? You know? No. On the other hand, I know Ohm's law. Could I look at the current flow that's going through the injector and know what the volts are applied and then figure out what the resistance is using Ohm's law? That might be a lot easier. Especially some of these injectors are really buried, but the wire that has the power going to them, I can get to, fuse, relay, something like that. And then I can monitor my voltage, and I can use a current probe to monitor the current. Well, if I know how many amps and I know how many volts, can't I figure out the resistance? And that's the real resistance while it's working. Or I could take everything apart, do this, and hope for the best.
Yeah.
Okay, so I can do a lot more work and get less information, or do less work and get more information. I like door number 2.
Yeah.
So in order to use an ohm meter, the component tested must be isolated from the circuit. Is that true or false?
True.
True, absolutely. So let's look at some continuity testing. Again, I'm using an ohm meter. So here, if I've isolated it and I've done continuity testing, I can see I have OL, which stands for out of limit, means it's open, it's not touching. Here I have 0 ohms resistance, but what? I'm shorted from one circuit to another. So if I did this test, wouldn't I get the same reading if I move the red lead to here or move the red lead to here as I have here? It'd be 0 everywhere because it's connected everywhere. It doesn't mean it's working right. It doesn't mean it's good. It just means it's connected. Here's another example here where we're checking, and yeah, I have continuity with ground. So I have a wire, and yep, it has ground on it. Okay, well, think about it. If it's an open circuit and I missed something, I didn't isolate everything, would I see ground through a load and still have continuity? Yeah. And if I have multiple loads, that resistance drops down to a lower and lower number. If it's something like a light bulb, I'm going to be pretty close to 0. Because light bulbs only have 1/4 of an ohm resistance, 7/10 of an ohm resistance. Very, very low. And the key thing here is the wire tells me if it's open, but it can't distinguish between degrees of good. Yep, we're connected. Will it work? When I went to school, we were taught to test everything with an ohm meter. I can't tell you how many hours I spent trying to fix cars and not understanding why it wasn't fixing and why I was getting weird readings and everything else. Because when I started, we really didn't have scopes the way we do today. We didn't have the tools we have now. As complicated as cars have gotten compared to where I started, the tools are so much better. I mean, just infinitely better tools now.
That's awesome.
You know, and I think that's why I'm still excited. If I still had to fix cars the way I did in 1985, I don't know if I'd have been able to stay in this business. I mean, it was just brutal. It was frustrating. We got very little knowledge, both from manufacturers and people teaching us how things work because they really didn't know and didn't tell us. Or we were told we didn't need to know, that's engineering. And we had horrible tools. And even with the good tools I have today, if I go work on a 1980 or 81 car and got to open the manual up, the information in the manual is horrible. It doesn't tell us the things we need to know. It doesn't. So we get more information now and we have better tools now. So our car's way more complicated, absolutely. But we have so many more resources now. And I would argue in many ways, they're easier to fix because now I can just be more disciplined and utilize my resources because I have so many more tools at my disposal.
It outweighs the complexity of new cars.
It does. And even though things are really, really complex, once I get down testing to the point of this is the part I replace, I really don't care what's going on inside. I've proved it's bad. I know what it's supposed to do. It's not doing it. I'm done. And so a lot of that complexity is at a level that we no longer service. When I started this business, we rebuilt alternators. We rebuilt starters. I worked at a shop where we rebuilt water pumps in the shop. Now what? Everything comes in a shiny new box. So where I used to really have to know all the pieces inside and how it works, now I need to know how to test it to prove it's not working inside. Just a different level. So current testing. There are two methods for measuring current. One is directly by placing the amp meter or the amp meter function of the DVOM inside the current path in series with the circuit. The other is indirectly by measuring the strength of the flux lines around the circuit with a shunt or inductive current probe. And we normally use inductive current probes. No automotive meters use a shunt anymore. So I have two settings. I have an amp setting and a milliamp setting here, and a microamp setting. So we can see here, this has a limit and this has a limit. There's two fuses inside. This one's only good to 400 milliamps, and this one's good to 10 amps, depending on which lead I put it in. So if I use my black lead on common and I move my red lead over to here, it's like just having a wire with a fuse in it. Which means that if I hook it up from battery positive to battery negative, I blow the fuse and the meter stops working. These fuses are 10 to 15 bucks each. So what happens a lot of times is someone may measure amperage and they forget to move their meter lead back over to this side for volts and ohms. And all it takes is just a second of hooking it up to test for voltage and you blow the fuse. And that's one reason why I don't like the Flukes for doing amp testing, because when we do this in person, everyone blows fuses. And I can't afford to run a class. So I use some different meters for that, that use cheaper fuses. That's also why we use inductive clamps. So an inductive current clamp is pretty slick. What it does, and I need to get another picture where I got a little better blow up of the graph. So these can measure from about 1 amp up to 600 amps, depending on it. And if we look here, they actually have a conversion. So here, 1 millivolt equals on this one 100 milliamps, or 1 millivolt equals 10 milliamps. Some of them 1 millivolt will equal 1 milliamp. So what we do is I no longer use the amp meter selection on the meter or the scope. I just plug the tool I just showed you into the common and the volt right here, 2 leads. And then it tells me if I put my scale on millivolts, here's how much a millivolt equals. A millivolt equals 10 milliamps. So I'm just going to look at my voltage scale and it's going to tell me how many amps I'm using. So again, it's all about the number, right? Get your head up. So your meter or your scope is showing you volts. I just need to understand that's amps, because this measures the amps going through the wire, converts it to a voltage at a fixed ratio, and then I look at voltage on my meter or I look at voltage on my scope. And these probes are pretty cheap. This one here, very popular probe, I think they're about 80 bucks. That's not that many fuses, is it?
No.
You know, and I'm not going to blow any fuses using this. Plus, the cool thing about this is I don't need to take anything apart. I just hook this around the wire I want to test. This is the tool I was talking about for measuring injector resistance.
It works on battery, the two?
What's that?
Is it to work on batteries?
Yeah, it has a 9-volt battery in it. So, and that's why you see the little low battery and power lights here to let yourself know. And then this 0 button right here, when I plug it into a scope or a meter, all of them, I might have a little bit of rounding error. I push that, it zeroes it back down to the meter reads 0. So I'm accurate. And so like this is a low amp probe. This one only goes to 60 amps. I might have another one that goes to 400 amps or 600 amps to make them up to 1,000 amps.
But where is the scale, Brian?
What's that?
Where is the scale of the inductive meter?
Right here. See where the switch is? There's 2 scales. One millivolt equals 100 milliamp. 1 millivolt equals 10 milliamp on this one. It's kind of hard to read. I need to grab another picture and put it on the slide. Normally in person, I have one I hold up and pass around, so I haven't had to do that. But yeah, I need to show you that. And I may even, I don't think I have a scope pattern on this presentation. I should probably build that in. I may try to do that this weekend so I can show you guys on Monday. But these are slick because now what? If I know how many volts I have at the source voltage, and I put this around the wire going to the injector, and I put it on a scope because it's a very fast pattern, I can tell you the resistance of the injector. That's pretty handy if the injector is buried under a valve cover and it's 4 hours to get to. You know, a lot of cars now use what's called direct injection. Much harder to access components, much more expensive components. You know, I want to be able to test them all the way back here, not having to go all the way into, especially when you test something, do you know that's the problem, or are you testing it to see if it is the problem?
Ladder.
Yeah, the latter. So I don't want to spend 2 hours to go do one test. I want to be able to do a test as quickly as possible to figure out if that's where my problem is. So what is the maximum amperage that we tested through a meter before a fuse may blow? And the number I'm looking for here is 10 amps. Most meters only have a 10 amp internal fuse. We saw that. Back here, I pointed out there's 2 fuses. I was looking for the 10 amp number right here. If I flow more than 10 amps, I blow the fuse. So I don't use this for many things. The only thing I do this with is what's called parasitic draw testing, when I'm looking to see why a battery goes dead. And even then you got to be careful, because if someone opens the door or turns things on, you're going to blow the fuse. But that's about the only time I use that function. And I don't use my Fluke for that, which is what this is, a graphing digital multimeter. I use a scope. I use a graphing multimeter because A, the fuse is 25 cents and I've got 1,000 of them. And B, it's way easier to change. And C, I get a movie of what's happening instead of just a number that keeps moving. So I have one of these. These are expensive. This is a Fluke meter. You know, a loaded Fluke meter like an 88 is like $400. I couldn't afford it back in 88 when they came out. I have an 83 or an 85. I can't remember which. It was still over $300. I hardly use it. I use my graphing multimeter / lab scope for everything. And I talked about that the first day. So direct testing, if I'm going to direct test, what I need to do is I need to, in this case, I took the fuse out. I now have an inline fuse holder. I have my meter, and you see where it's actually going right through the meter, coming down to here to what? Power up my injector, and my computer turn the switch to close it to turn it on. So my current is flowing. My circuit now comes from here all the way through here, all the way through my meter, all the way through my load, through my switch to ground. So you can see what would happen. What do you think happens if you take this red wire and put it to battery positive and the black wire and put it to ground with just that in the middle? Do you think that's going to melt in a hurry?
Yep.
Yeah.
That was a quick $15. Plus, these are a pain to take apart. So that is, but that, people have a hard time visualizing that sometimes. And even after doing this, people still blow fuses and meters. And that's a real issue. It's a real issue we have at the school when people connect meters up incorrectly, or they want to measure amperage, so they put the amperage probe into the amp button. No, the amp probe outputs voltage. We need to put it in the voltage connector. If I want to do direct testing, then I use the amp meter function in the meter, and I hook it up in series, which means I need to break the circuit open. An amp meter must be connected to the circuit being tested in which of the following ways?
One,
series. So here we go, incorrect connection. I took the injector out, which is my load. Now, is there anything stopping current flow in the circuit? No. So I took the injector out, hooked the amp meter up. Now I have a dead short when this closes and a very sad meter. Don't
He's
make your
dead.
meter sad.
or dead.
Wow, poor meter. And you see his poor little fuse. So here is another incorrect measurement. I'm measuring in parallel. I'm going from one side of the fuse to the other, but what have I done? I've created a parallel circuit. Now current can flow what? Through the 10 amp fuse and through my meter. And we know what happens if I create a parallel circuit. Does everything go through either side? No, it what? Divides it, divides the current flow. So I'm not going to get an accurate reading. If I wanted to be invasive and test the component. What's that? Okay.
I have a question, Mr. Brian.
Yes.
Where you where the meters are, the red and the black, is that the incorrect place to put it, or shouldn't it be like on the top or something?
I'm sorry, one more time.
Okay, this screen we're on now, where your leads are they in the incorrect spots or something?
Yeah, they're in the correct, incorrect, because I've made a parallel circuit. I need to test in series so all the current goes through the meter when I want to use the amp meter. Here I'm testing in parallel like I would for volts.
So if we were testing this, we would have both the little pins on the top of this 10A thing, right?
Right, exactly, but that would still be an incorrect connection because it would be in parallel. What we need to do is be in series like we are here, where we take the fuse out and put the meter in place of the fuse.
Okay, gotcha.
So we remove the fuse.
Right, remove the fuse and make the meter part of the circuit. Here, the meter is not part of the circuit. It's not the only part of the circuit. It's a parallel circuit. We need to keep it a series circuit. Does that make sense, Gary? Okay. I'll take it as a yes. I see the mouth move, but I don't hear nothing.
So this is when we're checking amperage, right?
This is when we're checking amperage, and that's why we normally use inductive clamps, because it's kind of quicker and easier for a lot of this stuff. But we do occasionally still hook meters up where we need to hook in series and use the meter. So I always want to make sure that I go over this pretty carefully, because this is something that's important. This is real world. And let me tell you, you're in a shop and you grab your boss's fluke meter and blow $30 worth of fuses out of his meter, and he probably doesn't have a spare, he's going to be mad. So I try to make sure I spend some time with this. And if it's your own meter, then you'll be mad at yourself. So here's an example. If I wanted to use the amp meter to test the fuel injector, we disconnected the connector. I used a jumper wire on one side, and my amp meter is my jumper wire on the other side to kind of illustrate I got to be in series with the circuit. You can see why inductive clamps are so popular, because all I got to do is clamp around a wire. I don't need to take anything apart. And I don't blow a fuse. So you see why, for that 80, 90 bucks, it's a real attraction for people in their tool arsenal, because you get it. And one of the things people don't realize, like the first one I bought, I paid over 300 bucks because it's red and it says Snap-on on it, and it went with the Snap-on tool. What I didn't know until years later is I could have bought any of them and there's a conversion, and it would have worked just fine, and I could have saved 200 bucks. But what do I always say? Knowledge is power, right? If I understand how it works and know what I'm getting, now I can figure out what do I need to buy on the premium brand, and what can I buy something else that's going to do the same job and spend a fraction of the money. So when testing for larger amounts of current, what type of probe should be used?
Inductive.
Inductive, absolutely. And what we're going to start with next time, and I'm going to kind of introduce you to this a little bit, is what we're going to do is we're actually going to trace this circuit. And this is a blower motor circuit. And this is my fuse. This is my HVAC control assembly in the dash. And then this is my blower motor resistor. And this is a blower motor relay. And here's a blower motor. So the blower motor is the motor for air conditioning and heating that we have inside the car. So if I trace this through the low circuit, M1, I start with here and I go through and I hit my first resistor. I hit my second resistor. I hit my third resistor. And then I come up and hit my blower motor. Am I using voltage each time I hit this resistor?
Yes.
Yes.
Yeah. So that means what? I have less voltage for my blower motor. That's why my blower motor goes slower. If I wanted to go fast, I'd have to go straight to it without any resistors. So it got all the 12 volts. So as we can see my different speeds, if I'm over here on low, I'd go through one additional resistor. If I'm on M2, I'd go through one less resistor. So as I go through different numbers of resistors in my series, more voltage is available for my blower motor and it goes faster. Is that making sense to everybody?
Yes.
Yeah.
And we've controlled multi-speed blower motors like this for 60 years.
Wow.
Okay. This is, you know, some new ones now we're actually in the blower motors a module and we're using more computer technology. But this basic function we have done and continue to do today on many systems. This hasn't changed. This is also, if I go to high speed, I don't go through the blower motor resistor at all. In this case, my high speed comes up here. Oh, it turns a relay on. So that's the load now. And it has a whole separate fuse with more amperage that comes through the switch to make the blower motor on high speed. Because as I get rid of resistance, I'm going to flow more current. And this is only what, a 20 amp fuse over here, I think? And over here is a 30 amp fuse. So on high, I need more current because I have less resistance. That's also why I might have a car that, oh, low speed doesn't work, but the next speeds do. Low speed usually burns out first because it has the most heat, biggest resistor in the resistor block. So if I have a car that maybe, you know, 1, 2, and 3 don't work, but I mean, low 1 and 2 don't work, but 3 and high do. Well, the switch is working. This is working through here. I'm thinking I probably got a bad blower motor resistor. And so again, if I tested the blower motor resistor, aren't I kind of dividing the circuit? Because this is where all the different inputs from the switch go. And this is where the power out to try to turn on to the blower motor goes.
Excuse me, Brian.
Yes.
Where is the blower motor is used?
The blower motor is right here, and the blower motor is used for your air conditioning and your heater inside the car.
Oh, okay, I got you.
All right, so that switch that you're moving, you're either turning it or sliding it, where you got low, medium, high, or 1, 2, 3, 4 on the dash. That's what we're doing right here. We're turning the dial, and we're directing the power through. Am I going through 4 relays before the motor? I mean, 4 resistors before the motor, 3 resistors, 2 resistor, or 1 resistor before the motor. So we'll come back. We're going to start on this on Monday, and we're going to go through this. I got a radiator fan circuit. I got a bunch of circuits we're going to look at, and we're going to talk about what kind of voltages I should get at different places and apply some of the voltage drop exercise and that to this. Yeah, Matt.
Question, like it's on high now, so it's going directly to the motor, right?
Well, on high, it's actually going directly to the relay because the relay is now the load. If I'm on lower setting like here, the motor's the load. So we actually totally changed circuit design. Now the relay is the load, but the relay works the switch that puts you right. Full battery power to the blower motor. A lot of systems.
Okay, so now a question, because like I said, if you got like 1, 2, 3, 4 and high, right, or low,
right,
and it's not working, the blower is not working in 1, 2, and 3, but when you go to high, it works. That means a relay is bad, or?
It usually means the resistor's bad.
Yeah,
Number one cause, 90+% of the time, bad resistor. What happens is this resistor right here burns out. If this one burns out, nothing else in there works. Because it's series. So if anything's bad, nothing before the bad spot can work. So you're right, on most cars, this one's a little different because they're using a relay. Many cars, you got the first 3 settings, and the last setting goes straight from the switch to the blower motor. But what they did here, because it's a module, they're using smaller wires. That's why they used a relay. So that's something that they changed from a 70s and 80s and even 90s car to something that's a 2000s car. Now that we have a module, I need a relay for the high-speed fan. I can't flow that much current through it. Same basic design, but yeah, if I have a car that comes in and it's speeds 1 and 2 don't work, speeds 1, 2, and 3 don't work, even if it's just speed 1 doesn't work, first thing I'm doing, but high does, I'm looking at that resistor. And resistors are normally really easy to get to and test. So it's also way easier than taking apart the dash to get to the switch. It's one of the easiest things to get to, and it's most likely what's bad. I think I'll start there. Again, I'm lazy. I mean, I'll own it.
Just help me fix my Toyota.
Yeah.